I guess this is the first seminar in this term. So the talk is going to be a survey of work I've been doing with many people, as you see, over the last almost a decade now. And we'll spend many topics. I mean, it's really about connections with between my side of things, optimization and computational complexity, many areas of math, and you'll see what the subtitle means. I do really mean if it's possible that we can prove that P is different than NP using some kind of algorithm, looks like convex optimization, and we'll see why. I'll start really slowly describing one problem that we were interested in solving, and it's the singularity of symbolic matrices, and one algorithm for it. I'm explaining this in some detail slowly in the beginning, and we have 2 hours. And then we'll sort of do iterations, understanding what we did, and generalize and understand it better, and sort of repeat. But the very end, we have some complete understanding. Actually, we are now writing a book about this whole theory that developed here, which extends for a family of problems that I'll explain, extending the standard convex optimization tools. I know many of you know about it, and many maybe not. I'll explain it. From the Euclidean setting, which is a normal setting, it is applied to a geodesic setting where you work not over Euclidean space, but over Riemannian manifold. And I'll get to this and explain. That's sort of the best understanding we have so far of this set of techniques that we'll evolve here. Please stop and ask me questions if anything is unclear. This is just a list of some of the, I say math, and I want to impress upon you that it's really sort of surprising to us, just connected to lots and lots of areas of math. I'm not going to read this, only some of them I'll show, and some even in some detail. Of course, I come from this bottom part, complexity and thinking about randomization and de-randomization, low bound and optimization. But there are many areas of math that show up, and both as a source of tools or source of problems or source of application. Okay, so we want to talk about these problems and algorithms. So the problem, actually, there'll be 2 problems. The one I want to, but I'll have a toy version for it, and I'll discuss it first. The toy version, you all know, this is a perfect matching problem. What is a perfect matching problem? You have a bipartite graph, 2 sides, U and V, and some edges, some pairs are matched and some are not. And what you are looking for is a perfect matching, namely, if you, like me, have 3 kids, or even if you don't, you have 3 candies, and you want to give a candy to each in a way that will be compatible with these edges, then in this graph you can do it. So this is a graph with a perfect matching. Here's the graph which does not have a perfect matching. So computational problem, I give you a graph, does it have a perfect match? It's a classic problem. As an efficient algorithm, actually dating back, I think, to Jacobi in some paper he wrote on systems of ordinary differential equations. He needed to basically solve this problem. So there's a classic algorithm which is taught in all undergraduate classes, I think, in computer science, which is called the alternating path algorithm, and it's efficient. And so we seem to know almost everything we want to know about this. But we'll see that some new things for me certainly will come up. Anyway, there's a natural algebraic way to describe this question. If you look at the adjacency matrix of this graph, namely you connect, you have a matrix where you put a 1 if there is an edge between U and V and 0 if not. That's A sub G of the graph G. Then one way to describe this problem is asking whether the permanent of this matrix is positive. Well, the permanent is like the determinant without signs. So you sum over all diagonals, product of elements on the diagonal, and the diagonal is a perfect match if it has all one. Okay, so that's a description. Permanent, many of you know, is not a friendly function. Positivity of it can be determined in polynomial time because it is a perfect matching problem. Computing is tough. And Jack Edmonds, many years ago, had a great idea of another algebraic formulation of this problem. Namely, instead of ones, whenever there is an edge between I and j, put a single variable xij in this entry. Okay. And that's now a symbolic matrix, right? Matrix with variables. And he noticed that another way to say that G has a perfect matching is the determinant of this symbolic matrix does not vanish identically. Why is it true? Well, obviously, because if the determinant is zero, there is no diagonal that's not zero. But the determinants are signs. But because of the variables, if there is some perfect matching, this monomial will have distinct variables that cannot be cancelled otherwise. So, okay, so that's his formulation. But then he made a fantastic leap and asked the following question. He said, suppose I give you a matrix, not with a different variable in some entry, but just arbitrary linear forms in every entry. Can you then tell me whether, right, so there's a simple representation of such a symbolic matrix, you just write the matrix coefficients of every variable. Okay, so these AI are matrices over the field. By the way, I mostly deal with the rational field, but the question is interesting for every field. I'll give you the couple of coefficients and this singularity problem, which he asked, given this symbolic matrix described this way, does the determinant, which is the polynomial, vanish identically? And to date, we don't know the complexity of this problem. Just some simple cases like the previous slide. So that's what we are really after, and that we don't know how to answer, and you'll see why. So he asked whether this is a polynomial time algorithm. And a simple observation is that it does have an efficient algorithm if you allow randomness. Simply, choose randomly an integer for every variable, even from a small range, and evaluate the numeric determinant. This is an easy thing to do. I should stress maybe that computing the symbolic determinant, if you do it in any way we know, I mean, if you expand the determinant, it will take exponential time. You can expand it and check that all coefficients are zero, but it's not an efficient way. So we don't know a sub-exponential way to solve this problem. If you have randomness, it's very easy, right? You pick these random numbers, evaluate the numeric determinant. If the determinant was identically zero, you'll always get zero. If it was not identically zero, then the chances of landing with this variety are very small. So it's an observation of Lovaas. And so really we are asking, we have a probabilistic algorithm whether it can be de-randomized. We can remove the randomness from it. Now, why is it? It's an interesting problem. Why is it important? One reason, Valiant has a famous paper in algebraic complexity, where in particular, he shows that this problem, symbolic determinant, singularity of symbolic determinant, is complete for a class. It actually captures all algebraic identities. Every algebraic identity you get in the Arzelians all over algebra can be encoded in just this question, testing whether two formulas like Vandermonde identity or anything you can think about, whether two polynomials represented concisely by a formula or a circuit, whether they are identical, it's this problem. So this problem captures all of them. That's one reason. It has many, many problems can be encoded in this way. I will not get to this. But there is, sort of killer message that this is a problem we must understand. So this discovery about 20 years ago by Cabanes and Pagliazzo, and for those who never saw it, we'll spend a little time inhaling this. If this problem has a deterministic polynomial time algorithm, then something major happens. Something we have proven, something like P different NP. I put it in quotes because it's not exactly that, but it's something similar. We will be able to prove hardness and we have no idea how to prove hardness. That's a major open question of the field, proving difficulty of some explicit problem, and people tend to sort of capture this. So that's why it's important. We have this implication, but there is something strange about this implication. You see that if there is an algorithm, an efficient algorithm for a problem, this implies that many other problems are difficult. This seems to go in some wrong way. It's I will not get into this, but we knew of this phenomena, but so concisely for a concrete natural problem, having an algorithm for it implying lower bounds is sort of amazing. And that's the reason to be interested in understanding it and looking for an algorithm. Okay, questions about this? Or questions in general? Yeah, so this problem is about algorithms, de-randomization, and lower bounds, what we're after. And I said we don't know how to solve this problem. So here's a problem, and when we can solve a problem, we do what all mathematicians do, we change the problem. And so I want to tell you about the dual life of symbolic matrices. The question was a singularity question. I give you a symbolic matrix like this, ask whether it's singular. You all, like I did, assume that we are talking about commuting variables. And then the question of singularity, whether the determinant is zero is whether this symbolic matrix is singular in the field of rational functions over this variable. That's equivalent, of course. And that's what we know. We have a probabilistic algorithm, but not a deterministic algorithm. But instead, we are going to study the case where these variables do not converge. And immediately you should ask why this is interesting, and we'll see lots of reasons. The whole talk will give reasons to solve it and then to see what applications this said. But anyway, what was known about this? The first question is to ask is a serious question. Invert the symbolic matrix well. So you want an analog of the field of rational numbers, some completion of the non-commutative polynomials. Such a beast exists. It's called the free skew field, free non-commutative field. It's a complex object to define, so I didn't really define the problem, but you'll see elementary definition of this problem. We want to ask whether it's singular over this field. Even the fact that this is a decidable problem, it has a finite algorithm, was an open question for many years, and this was solved by Kohn, and he developed the whole theory method which we are using. Then with Rathenauer, he proved that it can actually be solved in exponential time, and that was the best known. For a long time, it seems like it's harder than the commutative case, but the main result I'll talk about in this hour is this paper with Gal Gurwitz and Oliveira from 2015, proving a polynomial time, designing polynomial time algorithm for this problem. So it became easier than the commutative case. This is the case of rational or characteristic zero field. Soon after came another beautiful paper with an entirely different algorithm, which solved the problem actually in polynomial time for every field. This Ivanio, Sklar, and Subramanian. And then 2 years after that, Hamada and Hirai found again an entirely different algorithm which solved this problem. So there are various algorithms for this by now. I'm going to speak about this one, which is sort of an analytic. The second is like the algebraic, and the third is some modular optimization type algorithm. Okay, so that's what we are going to do. That I described the problem. This is the problem we want to solve, non-commutative singularity, and now I want to talk about algorithm, the algorithm. And again, I'll demonstrate the algorithm first on the toy problem. The algorithm is called alternate minimization. You'll see why. Again, here's the problem we want to solve, right? And so I had already several definitions of the perfect matching problem. I want to yet give another description of it. So for that, I need to talk about matrix scaling. It's a different type of problem. The input is a non-negative matrix A. I just want to remind you what a doubly stochastic matrix is. A doubly stochastic is row sums and column sums L to 1. It satisfies this equation. What do you do if the matrix is not doubly stochastic, but you want it to be? That will be the problem. And the question, what is allowed to do? If you want to make it doubly stochastic, what are the rules of the game? You can try to make it doubly stochastic by multiplying rows by constants and columns by constants. Okay, in other words, pre and post multiply by matrix, diagonal matrix. And more specifically, I'm going to define the problem. Doubly stochastic scaling of such a matrix is to decide if there exists such diagonal matrices which make it be almost doubly stochastic. This turns out to be the right definition. Almost, I mean, for any epsilon I give you, you should be able to make the row sums and column sums add up to 1 plus minus epsilon. Okay. And it's the right definition simply because this makes it equivalent to the perfect matching problem, or more generally to the question of whether the permanent of this positive non-negative matrix is 1. This proof is not difficult. Okay, so we have another representation of this same problem. We want to solve perfect matching. By the way, this came up independently in many contexts. It's usually attributed to Synchron, even though there are papers about it from the 30s. It's called the matrix scaling problem. It's related to many areas that I will not talk about here. Okay, the problem is clear what scaling of a matrix is. So we want to ask whether it's possible or not. And what algorithm are we going to apply? In fact, Synchron and many before and after. It's here's the example we run through, but it's hard, right? On the one hand, it seems like a fair problem. We have about 2 constraints and we have about 2 and 3 parameters to play with. So, but they interfere with each other, right? The rows and the quadrant. So here's the genius or naive idea, the greedy idea. It's hard to do simultaneously. So let's deal with either the rows or the columns. Let's solve half the problem first, and maybe we make some progress. So let's make the row sum 1. This is easy, right? We just divide by the row sum. So scale the rows. Okay, we scale the rows. The columns are not scaled. So let's scale the column. Okay, scale the column. Now the rows are not. So let's scale the rows again. And some of you may see what's happening and some of you may not, but anyway, that's what happened in the limit. It will alternate between these 2 possibilities. It does not converge. On the other hand, the graph I started with has no perfect matching, and well, we'll see where this goes. But in this example, the graph of the perfect permanent is 0 and there is no convergence. Okay, that was one example. Let me just write down the algorithm. More specifically, as an algorithm, I mean, what we will try to do when we are scaling, we'll just take the matrix and do a row scaling and column scaling in the obvious way. So this is the alternate. Minimization doesn't matter. Yeah, that's the alternation in the name, alternate minimization. Many such algorithms have this behavior. It's generally a heuristic. Now let's try it on another example. This was a graph that has a perfect matching. Of course, you can see it on the anti-diagonal. And let's try the same thing. It represents this graph. So we scale the rows, scale the columns, scale the rows. You might see what this is going. In the limits, it will look like that. So it converges, and this graph has a perfect match. And of course, these are representative examples. That happens always. So I'll show you an analysis of the algorithm. In fact, an analysis from this paper with linear randomness, a different analysis than the usual one, which was very illuminating for us. So just to complete the description of the algorithm, you run it for n cube steps, that it probably will be polynomial time. It will be enough to determine whether it's converged or not. And if when you stop, let's say the rows are scaled, you look at the columns, and if in whatever norm you like, infinity, let's say, the column sums are close to the O1 vector, then say yes, the permanent is positive, and if they are not, then say no. Okay.
Little question. So, does the algorithm always converges to something if there is a perfect match?
No, you saw an example. Oh, if there is a perfect match, yeah, that's what is a theorem. Yeah, exactly. It's always, yeah, this algorithm works always.
No, I mean, yeah, but in this statement, it's not written whether it converges to something.
Yeah, it does, it will converge.
And the thing it converges to is telling me something about perfect matching?
It's a very good question. And in the case of perfect matching, in this problem, we don't know. In the case of the real problem of non-commutative singularity, we do know. Here it's a great question. It will converge to some doubly stochastic matrix, And the reason this paper looked at this problem and this algorithm was in order to find an approximation of the perfect match, of the permanent, like the number of perfect matches. And all it gives you at the end is an approximation factor like e to the n, which is pretty bad, but we don't know much better.
So the question was like, what does it converge to? If you work through some duality, it like the thing it converges to is something like the fractional matching with bit entropy is approximately what it converges to.
Yeah, you can.
If you work it out, that's kind of what it is.
There is a geometric program you can write to describe this problem, and the objective function is minimizing KL divergence of your matrix to the polytope of doubly stochastic matrices. But maybe I will not go. More questions? Yeah, so the main point I want to make is that there's a really simple analysis of this algorithm. Really simple. From this paper, how do you analyze an algorithm like this? In general, I mean, it's really a dynamical system, right? It generates a sequence of matrices. And you want to say something happens, it converges or something. And you need, for analyzing convergence of some dynamical process, you typically need some progress measure, the open function, whatever you want to call it. And you will simply pick the permanent itself as the progress measure. Okay. We have a sequence, A1, A2, things we generate. And we want to argue about the permanent. And whenever you have a progress measure, there are three things you need, and then it works. And here's our origin. First, the permanent throughout the process is the smallest one, simply because row sums are one or column sums are one, and permanent is the smallest product of the sum. If you are not too close to the doubly stochastic case, then the permanent actually grows by a significant factor, something like 1 + 1 over n. So you make progress fast towards where you want to go. And the last one you need is that but if the permanent was 0, it will never change value scaling. If the permanent was positive, you want to say, I start not too low. The value of the permanent is not too small. And this you can arrange, it's not trivial, but it's easy. Anyway, so you start exponentially small, which is good enough if you progress geometrically, right? So this will lead to a polynomial time algorithm. That's the whole analysis. And the middle step is just a simple arithmetic mean geometric mean inequality. Very simple. Okay, so we have a simple analysis of the simple algorithm, it's in particular so perfect. So that was a baby case and described in this type of algorithm. Okay. Yeah, actually, all the analysis here was the proof of the AMDM step. I don't think I really do this. Yeah, basically, I put here the proof of the AMDM. Yeah, let's repeat it. You see, it's a one-line AMDM application. It basically says that AMDM is far from attaining its will have equality only if all the numbers are the same. If they deviate from being the same, then there is a gap and you get the progression. Okay. I want to mention that there are generalizations of this problem, of scaling problem, which we'll get to at the end, I hope, which are non-uniform. I mean, in general, think of matrix as describing a bivariate distribution, and you want its marginals to be something. Beforehand, we want the marginals to be all the same, right? That's a doubly stochastic case. But you may want them to be some other thing, some vector, P and Q. That comes up in practice, and that's called non-uniform scaling. So we'll get to this, but that's a computational question, and it turns out, yeah, here it's not related to matching, but more to flow. It captures more general marginal problems. You can have multivariate distributions like in a tensor and so on. You can ask the same question. But anyway, for this matrix problem, even for different vectors than all ones, the same algorithm. Okay, so we've done the baby case, and I want to move to the general case of non-commutative singularity and tell you about operating scaling. So what will happen? We'll have the same analogy. We solve bipartite matching via a formulation of it called matrix scaling, and we will solve non-commutative singularity by a formulation of it which is called operator scaling. It was introduced by Gurvitz, and in fact, a lot of ideas, torches were introduced. In fact, immediately after that paper with Linar and Samornitsky that I mentioned, he just had a quantum generalization of it. But the analysis didn't quite work, and that is the paper that I mentioned with Gurvitz and Oliver. So in general, you want to quantize something. It often happens in this cartoonish way. So we want to generalize the matrix. So I'll define operating scaling more formally, but just in spirit. You go up in dimension and you change L1 to L2, basically. So here we have the positive matrix A. In the operator scaling, we have the tuple of matrices. Then you move from L1 to L2. You need a definition of what double stochasticity is. There is a very natural definition for a tuple of matrices. It's written there. Some AIA transpose is the identity, and the dual is like columns and rows that transpose of it. So we have a natural notion. And another thing that goes up in dimension is what you operate with. If you operated with diagonal entries, I mean, vectors go to matrices. So you would operate, you would try to scale with non-singular matrices, general non-singular matrices. Here's the definition. So what Gurvitz did, he first of all made this connection between the problem we want to solve, or the problems we want to solve, which are about singularity. We have a symbolic matrix, and we want to know whether it's singular, commutatively, non-commutatively. He was interested in the commutative case. But the input is a couple of matrices. And also for this new problem, operator scaling, which really comes from quantum information theory, is the same input. So at least it's the same input. What about what we want to do with it? Well, just define what is the, in what way a tuple captures an operator. It's a tuple of matrices defines what's called the completely positive operator as a linear operator on matrices P, right? So you get input P and you apply this AI P diagram to get the output. In particular, you see that it takes PSD matrices. The PSD matrices, which is imported in quantum information theory because they do, these represent quantum states. And I mentioned the definition of double stochasticity. And here was the, Lewis, ingenious idea, just written in different ways. If you input this top of the identity matrix, you get out the identity matrix. That's what it means to be doubly stochastic. Just like in the matrix scaling case, you input the one vector, you get out the one vector both on the left and on the right. It's really an analogy, a quantum generalization. And yes, can we or cannot, we are given an operator, a type of matrices, can we or cannot we scale it? And he figured two things. One is that maybe there is a connection to, okay, so that's the operator scaling problem. And he believed that there is a connection to the singularity problem. And in fact, solve this implication. We cannot scale means that the matrix is commutatively non-singular, but it doesn't go both ways. And in fact, one of the starting points was realizing that it's really equivalent to the non-commutative singularity problem. That's one part of it. But the other thing that he realized is that this scaling problem, one may hope to apply the same alternate minimization. It's a scaling problem. And you act from the left, from the right, it looks like maybe you can get an efficient algorithm. So let's look at the algorithm we proposed. He proposed the exact same algorithm. When you want to scale, scale from the left, make it doubly stochastic in the maybe row sense, and then from the right in the column sense. It's very easy. You don't need to read the formulas. The algorithm you should looks identical as the previous algorithm. Okay, and moreover, he suggested the progress measure that will have similar properties to the permanence, so the MGM will work and everything. And he suggested a measure called capacity. It's basically you look at the infimum of the determinant of the output divided by the determinant of this component. Here you don't have to remember it. The important thing is that, like in the permanent case in matching, it's the same property. It's commutatively singular when the capacity is zero, commutatively non-singular when it's not. So it has all the properties, and moreover, he said, let's analyze it in the same way. Capacity is bounded by one, in this whole sequence generated. Capacity grows if you are not close by the same AMDM argument. And the last thing you want to say is that when the capacity is positive, it's not too small. You start, if it says, what to say this exponentially small, and I progress geometrically, I finish in polynomial. So that was his hope, and this he couldn't prove. And that was the main thing that we proved, and I want to explain to you how. But it's completely analogous. Okay, so the main difference, so in the last line, it was easy in the case of here you need some theory when it comes the need for invariant theory, realizing the group action here, this measure, so the permanent was sort of what's called semi-invariant, and we need tools and the results from invariant theory that I will explain and describe. Okay, so that's but the template for the analysis is essentially the same as before, and you just need this bound. This now it became not an algorithm, but just one analytic property. Okay, now so we this was figured out. We have a polynomial time algorithm. That I showed you already two problems for which the input is a type of matrix. And there are two problems which look completely unrelated, right? And one from quantum information theory and other from the algebra. Actually, I listed here 6 different problems that have the same input and coming from very different areas. And they're basically all equivalent. The sixth one is even a special case of the others. I'll talk a bit about some of them, but you immediately get, polynomial time algorithm for all of them. There are different problems from different fields that people worked on independently, and they all have a polynomial time algorithm. In some areas, they are just interesting problems. In other areas, there are fundamental problems. Yeah, so I'll talk about this one, which is really the world problem for the free skew field, and this problem, which is about analytic inequality. Okay, so I'll just show you in some detail. I'll now move to some applications, and then we'll return to the theory and generalize it. Questions so far?
Another question. Do the permanent and capacity type analyses extend to the non-uniform marginal case?
Yeah.
But with the same.
You need to work more. And in the case of capacity, you see that we'll get rid of both permanent and capacities. We'll have one measure. Yeah. But I just want to talk about application mainly because to show what the variety of problems this kind of algorithm solves. Here it is all about proving identity, or proving identity. And later we move to proving inequality, which seems to be a totally different ballgame, right? But this is in the non-commutative case. So again, back,
What's the joke with the horse?
Well, I don't know. It says the older methods. But if you have a suggestion for a better one, what is not pointed older method. So we have a field and we have some non-variables over it. I want to describe the word problem for this skew field. So I said that these fields are completions of non-commutative polynomials. So polynomials are just polynomials like that, where the order of variables in monomials method. So x, y, not y-axis. Just to show you that it's really more complicated than what you are used to. So the field, basically another description of it is simply the elements is all formulas, addition, multiplication, and inverse, like formal expression, like x inverse plus y. If you look at this expression, you see that unlike the commutative case, you cannot write it as a ratio of non-commutative polynomials. You cannot. That's something you should try to prove. So it's something else. It's something more complex. In fact, it's more complicated than that. These expressions here have nested inversions. Of course, you can also in commutative variables have nested inversions, but you can always simplify them. Any expression is a ratio in the commutative. Here it is not. It's a very important difference of Schopenhauer to show that there are expressions with unbounded nested inversion which cannot be simplified. Okay, so it can go higher and higher. Of course, sometimes you can simplify, and that's exactly the question of proving identity. Here's one famous identity. It was identity. It has to do with the fundamental theorem of projective geometry. But anyway, here you have an expression with nested inversion 2, and it simplifies to nested inversion 1. So I give you such, or why, how did he solve this? How did he know this? Or how do you know that an expression like this vanishes identically? And that's basically the word problem. You tell whether an expression vanishes. And that was the core problem. And as I mentioned, he proved it was decidable, and what we show is that actually it's a polynomial time. So that was one application. That was proving identity. I want to tell you about proving inequality. You get this job?
It's too small.
Too small. That's okay. I don't know, just pick them up. So, what's inequality? Okay, so I want to tell you about a very important family of inequalities, was defined by Bostrom and Reed in 76. I'll explain more, basically, or maybe not, I'll give examples. Basically, inequalities which look like the integral of a product is a integrable. I'll give you examples. Well, I'll soon give you detailed examples, but just to say, this class of inequalities captures lots and lots of inequalities you've seen from different areas, from geometry, from geometry of numbers analysis, like hypercontractivity and combinatorics with Whitney, or maybe entropy, of course, procedural and all. So let me show you. And that's what we aim to try to prove using the same algorithm. Just to make sure that this looks like the template I showed, an integral of the product. The function that was the node of the product of the functions. So this happens with particular norms, two norms, right? We'll care about the norms. And in this case, if there are other norms for which this inequality is satisfied, we know that there are, right? It tells us we satisfy this. That's a Herbert inequality. That's one example. Another example, yeah, and there are no other norms. This is important. You cannot find other norms for which this particular statement will be true. And there's a constant one in both of them, and it's the optimal constant. You cannot improve Cauchy-Schwarz or Herbert with a better norm. Here's another inequality. It sort of goes in many dimensions. In 2 dimensions, it just says that the area of a set in the plane is at most a product of its projections through X and Y coordinates. It's called Loomis-Whitney. Here it is in 3 dimensions. You have a 3-dimensional object set S and its projections to 2 dimensions. And that's the analogy. The volume of the set is at most a product of its areas, but squirrel, and it has an entropy version, if you want. And it looks like this. Why? It's the same template. We have 3 dimensions. We have functions from, or any function you can. So what I'm saying will generalize this. Any function you take from the plane to the non-negative integers, we have the following Loomis-Whitney inequality. Again, an integral of this product is mostly L to no product of this function. And you can ask yourself if there are any other norms for which this is true, like a generalization of Herbert. Here there is none, right? And also here the constant is 1, happens to be 1. So here there are no other, yeah, so that's interesting. Sometimes you can have a Herbert analog, sometimes not. I'll give you the final example where you see the constants that can be with the same Loomis-Whitney thing before we projected orthogonally. You can ask about projections in several directions. Let's say here you are set in the plane, and you project it to the x coordinate, y coordinate, or maybe x1, x2, and this diagonal. And you ask what's the relation between this projection and this. And here's a Young inequality, a special case of Young inequality. You get this inequality, the area is most this product to the 2/3 power, and there is a weird constant ahead, and it's the type constant. So he proved it. In fact, more generally, you can have again 3 functions, and that's the Young inequality. If you have this integral of this product, it happens to be at most this constant times the 3 half norms of its function. So yeah, it's getting there are many, many more. What my point is, yeah, here there are many other norms, and the constant change where you know, depending on the norms, and you would like to know when is such an inequality true and when what constant is there. And the way they look generally, these inequalities is just think of high-dimensional version. They are given by two types of data. One is this projection to the different. In general, there'll be to some Euclidean space from Rn to some maybe smaller Euclidean space and a set of norms, but it's more convenient to think of one over the norm than the norm if you want to see what's known. This is a template for the for these inequalities, and you want such an inequality to hold no matter what integrable functions you have from these spaces to non-negative integers. And it turns out that the feasibility region, if you want to know what norms such an inequality is true for, there's a characterization which gives actually a linear program for it. Elliott-Leib computed the exact optimal constant for every such inequality whenever it's feasible, or at least gave a characterization. We didn't compute the characterization. And it turns out that this problem reduces to operator scaling. I'm not going to explain how. So we can, for any such inequality, there's a polynomial time algorithm. You get this data and it tells you what the whether it's feasible, and we'll compute for you the optimal scaling, which will come out of the capacity. I have here the polyhedral description. I'm not sure I want to get into it, but I'll later describe a bigger set of polytopes, but I just want to point out that to know whether a point P, namely a sequence of norms, is in the feasible for this type of projections, B1 through Bn, generates a polytope with actually infinite number of inequalities. You have an inequality for every subspace of the Euclidean space. So it's a strange polytope, and you want to basically compute membership for it. And infinitely many, but because they are all integers here, exponentially many. Anyway, this is the kind of membership problem that the algorithm solves in polynomial for any such. Okay. Question. Anyway, bottom line, this algorithm also proves inequalities. It has more, maybe I have a joke for everyone. It turns out that then people started realizing connections of this operator scaling to other problems that we didn't think about at all. And I'll just mention them quickly. One is this basically geometric inverse problem, which is really nice, called the Paulson problem. Think that you have you're in RD, maybe it's 100, and you have n points, maybe n is locked. And what is a Parseval frame? A Parseval frame is a set of vectors. It's called the Parseval frame if this some VRVR transpose, this sum of rank one matrices deal with the identity. And so it's a decomposition of the identity. And their norm squared is D over n. That's exactly what you need. That's a normalization. But okay. It says they are somehow arranged really nicely in space. So that's a Parseval frame. And something is an epsilon Parseval frame if it almost satisfies these conditions. So again, you don't have to go into this, but their norm is very close up to epsilon to what it was, and their sum is very close to the identity. Okay. And here's the question that Paulson asked. He said, what's if I give you an almost Parseval frame, how? Actually, I have to move the point so it's exactly a Parseval frame. And there are Parseval frames, you can move it there, but you want to move it as little as possible, and it makes sense that maybe you don't have to move it much. And so it's a parameter of, so these three parameters, and the epsilon, and it turns out that, and it's not a difficult proof, that the distance they will all move, right? The distance will move the points you have to the points that are perfect. is polynomial in n, d, and epsilon, but there was a strong feeling that this n, the number of points, which may be much larger than the dimension, is not really needed there. And this was proved in this really amazing work, which uses the operator scaling and geodesic flows and smooth analysis and beautiful thing. It turned out that much less was needed. This was simplified by significantly with a much better bound by Hamilton and Moitra. By the way, Ankur Moitra is going to be here next, in 2 weeks. Yeah, he gives both Monday and Tuesday talks, and he's a great speaker, so we should all come. Yeah, statistics, well, that's another place where it came out surprisingly in modeling and estimating parameters of distribution. Let me just flash it because I don't want to talk about it. It turns out that operator scaling enters in determining whether how many samples will be sufficient to determine if you have a collection of models. There are 2 types of models here. You have a collection of models, and you want them its parameters. How many samples will enable you to tell whether to compute the parameters, whether parameters are unique, and so on. This can be done, was done in these papers by using operator scaling. And more generally, use of symmetries and invariant theory, which we will see in the next slide. Okay, so I'm done with applications. We are back to theory. And maybe, questions first. So I want to talk about how this evolved, this from operator scaling to this geodesic algorithm. Okay, so now we want to somehow understand what we did and generalize. There'll be 2 rounds. I first want to go back to these 2 questions. And the problems and their algorithms, which were alternate minimization. And the first important observation was that they actually happen in groups. So this is the algorithm, and really we apply matrices or diagonal matrices or general invertible matrices. They are groups. So here we act on matrices from the left and from the right by what we call the closed group, the group of diagonal matrices. On the right, we act them by GLN, right and left. So there are group actions, and because of these group actions, we want to understand them. If we want, this happens to be the case here, it may be advisable to understand symmetries and understand invariant theory. So let me give you a crash course for 5 minutes, at least on the few elements I will need for invariant theory. Okay, so what is it about in general? Symmetries, group actions, orbits, invariants. There are several examples here, graph isomorphism. There is a group action, the symmetric group that moves one graph to another. Another famous example, playing pool. I mean, you kick the white ball and then it evolves. So here the group acting is really time. It's just the time evolution of the state of the billiard table. So you think of some dynamics. There's the group moves an object about. Here you want to move from the left figure to the right figure by cutting and shaping the pieces without overlap. I don't know exactly what the group is here, but there is some kind of group. And then you want to study, these orbits, what the evolution goes through. And then you want to say, even though there is dynamics, some things don't change, right? These are the invariants. So, for example, in the bottom case, it's a famous theorem of Dan that there's only one invariant. Of course, area is preserved if we don't overlap the pieces. It's the only invariant that's preserved. And by the way, this is not true in 3 dimensions where you ship for this. Yeah, there are two invariants. Not only volume, but there is something else. Here we know from high school physics, energy and momentum are in fact the only invariants. Here, of course, we don't know the invariants. I mean, by algorithm for the hydromorphism, but we don't really know what the invariants are. So in this talk, we care about linear groups, the groups of matrices, which act on vector space. There are these stars to say the linear group should be reductive and the actions should be algebraic. Don't worry about this thing. Just think of the actions. You'll see they're all natural. And the nice thing about this setting is that there is a very strong connection between algebra and geometry or algebra and analysis, and we will see this connection being extremely useful to us. So here's a crash course. We have a group, think of a matrix group acting on a vector space. Of course, if it acts on the vector space, also acts on polynomials in this space, in these variables. So first notion which is important is the orbit. I give you a point, a vector. All the points it can move to by group element. And because we will be in continuous space over rational, over the complex numbers, let's say, will be more convenient. We look at the closure. Okay? We look at the limiting. We look at all the limit points of the second very important notion is the invariant ring. These are all the polynomials that do not change under the group action, right? So whether you apply it to V or you apply it to G times V, move V by G, it remains the same. Turns out that all invariants in these cases, the algebraic setting, are polynomials. So it's a ring, obviously, it's an algebra. Here's a simple example that you all know. If we had a symmetric group acting on vectors simply by probability coordinates, what would be the invariant polynomials? Yeah. Symmetric polynomials, amazing. And moreover, they are all generated by very few polynomials, and this will be important. Here they are generated by n polynomials, right? It's elementary symmetry. Here's another example. Suppose we do this left-right action, let's say by S and N, where we see S here instead of G. And this means determinant one. Determinant one matrix, so here's the vector space of all matrices multiplied by the left and the right by determinant one. What would be the invariant? Yeah, the determinant, and only the determinant. All other invariants are generated by the determinant. So again, we have a simple generating set of log degree. And in fact, this is not a coincidence. Herbert famously proved that all invariant rings in these cases are finitely generated. This is the same paper where he proved the null-standard theorem and the finite basis theorem, and which were lemmas towards this theorem, but of course, took important life of their own. But once we know that, we can ask, what is the generating set? How small degree can it have? And having degree bound became an industry, and we need this result. The last notion I want to make is the null cone. So what's a null cone? It's all the points that look like zero. Okay. If you look at the invariant polynomials when you apply, or any polynomial without free coefficient, you apply to zero, you get zero, right? So you ask, what are all the points that if you apply an invariant polynomial to them, you get zero? Okay. It's an algebraic variety. It's a very important set if you think about trying to compactify the space of orbits. You want to, or if all the orbits become a point. So these are all the points that will become the point zero. And the important connection here, that's an algebraic definition. By the way, these null cones appear naturally in places you've seen, only they didn't call them null cones. For example, in the second example, what is a null cone? What are all the points that look like zero? They are the singular matrices, right? Determinant vanish. By the way, if you change left-right multiplication by two matrices, you replace it with conjugation by a single inversible matrix, what will be the null cone? Anybody has a guess? Will be the nilpotent matrices. So anyway, natural sets you know about arises null cones of group actions, and many other sets arise. The important thing is that this algebraic definition has an analogous analytic one. Herbert and Mumford showed that a point is in the null cone exactly if you can derive this point using the group action as close as you want to zero. So zero is in the orbit closure of the point. Okay? There's a sequence of elements that will take you as close as you want to zero, which another way of saying it, and it's important for us, is that you can derive the L2 norm of the vector to zero, right? It's equivalent. That is really key for us because the L2 norm will become our universal progress measure for this algorithm. Okay, so far that's the crash course. And both of these, L2 as I mentioned, and the degree bounds will be essential for the analysis. Now that we have the definition of a null cone, I showed you already. So what's the membership problem? I give you a point, is it in the null cone? Does it look like zero under this group action? It turned out to capture many problems. We saw an important and singular matrices, but also the matrices that cannot be scaled, null cone operators that cannot be scaled are in the null cone by the group actions you've seen. But these problems were scaling problems. So what does it have to do with null cone? We'll see more explicitly why membership in null cone is dual to scaling. That's a major observation that was crucial to us. Okay, so here's one really natural generalization of the algorithm you've already seen. And in these papers, we really wanted to see what alternate minimization can do for us for more general settings. Let me just give you what maybe statisticians or machine learning people or optimization problems, people will tell you if they want to motivate alternate minimization, just to show that it's a heuristic that has many applications, but in most cases we cannot analyze. In general, if you have a complex function of many variables, we've seen only two variable functions before, but it's complex to solve simultaneously, but you happen to be lucky, and it's easy to solve these problems if you are fixing all parameters but one. So this is analogous to Roman scale. Then you can run this algorithm. You just iterate your cycles through the parameters and optimize them one at a time, hoping it's converted and converted fast. Here are some examples. Due to von Neumann, it's interesting more in the infinite case, but you want the distance between convex sets, like closed convex sets in high dimension. Well, it says just basically alternate projection. You just you alternate the closest point to the previous, and this converges. We don't know how quickly exactly. That's just one example. Nash equilibrium is another example. For many have seen it. I mean, it's setting is you're given a pair of matrices for, let's say, two people who want to compete with each other or play a game, and the Nash equilibrium is basically so you want this probability distributions on strategies to each player that will be each one as good as possible given the other one. So they have to satisfy. These inequalities are not important to read them. Of course, Nash's famous theorem is that equilibrium always exists. And people look for algorithms. We don't know have an efficient solution for it, but alternate minimization is sort of a natural heuristic, can do best response, which just, again, we have two parameters. Start with any distribution, see what's the best response to it, and what the other one best response, and this will be very similar to the previous picture. We don't have an analysis, a good analysis for this, I mean, beyond exponential time. The last one is, and you can try to do it for more players. I want to show that your alternate minimization is something that's familiar to you, even if you are not doing optimization, but you are doing sampling. This is a famous Metropolis algorithm. Suppose you want to sample from a probability distribution on a product set. How can you do it? Well, you can fix all parameters and resample one point, one coordinate according to the marginal distribution. So a simple example is finding a random legal coloring of a graph. Let's say coloring this with 4 colors. When you start with any coloring, even illegal, this will be fixed. You pick a random vertex, the top one, it's yellow. We want to resample this yellow in a legal way. So we are not allowed to use green, we are not allowed to use blue. So we sample and then we maybe randomly select the right vertex and we sample it. And this Markov chain is also an example of alternate minimization, right? And this is something we use all the time, or many people use all the time. Anyway, so these were just examples. Back to the algorithms we had this alternate minimization, 2 examples where there were group actions, diagonal or GLN actions from left and right. The most obvious generalization is what we started with is take groups in higher dimensions. And here it is. So think about acting on the matrices or just acting on a tensor in k-dimensional space. And let's say you act on fiber on each direction. So your space is basically this tensor. A tensor is a point in your space. It's a product space. And each group acts on one direction, one fiber. Rows, columns, I don't know how to call it. And let's say that every group is, either diagonal or invertible. Let's put the determinant 1 here. So you want to scale this, or you want to make all marginals uniform. You have to define what it means, the analog of W stochastic, KY stochastic. It can be done, I'm not defining it. And the basic thing is that if you run the alternate minimization in this setting, suddenly you have an analysis, in fact, convergent analysis, and it's efficient. You can get epsilon close to a scale, if it's possible, in this amount of time. Okay, polynomial in all parameters. The same algorithm. Now, as you also said, this is a non-convex problem. The domain is basically the groups, they are not a convex set. And nevertheless, you get it. And this actually comes up, it's not just an absolute generalization. There are special cases in many areas that are, have exactly this kind of representation. So they're all interesting. It's not that we solve all of them, because this analysis doesn't mean that sometimes to know when to stop, to see if you converge or not, you need to, the previous example, it was polynomial, inverse polynomial, but sometimes it's not. And, it's not that we have polynomial time algorithms for all of these problems. But I want to stress that the analysis looks the same. It's really the same. Just like before, and what you pick from your L2 norm is that just for your progress measure is the L2 norm. This is motivated by the fact that this scaling is really a null problem, and you want to minimize it. Here you want to ask whether you get to 0 or not. I wrote it here in reverse, but it doesn't matter. I mean, the important point is this gap. You want to say that if a point is not in the null cone, like if the matrix will not be scaled, then you have a lower bound on its L2 norm. And this happens to be really easy if you have bounds on invariant degrees of invariant polynomials, and also their height. So let me explain this. So this difficult thing becomes easy if you just know what you need to know from invariant theory in this very general setting. So what is the proof of this? So let me tell you what we need from invariant theory. So again, I want to prove that if you are not in the null cone, your L2 norm is big. Big, it means exponentially small, but not smaller than that. That's what we want to prove. So I mentioned that what invariant polynomials are, right? And being in the null cone means that invariant, we have all invariants are zero. So being out of the null cone means that some invariant is not zero. And it's sufficient to look at the invariant in the generating family. So there must be an integer invariant polynomial that's not zero. I should say that this alone is a way to prove that we is out of the null cone. But if you just ran over all generators of the invariant ring, maybe, you know, as far as we know, they are exponentially many or doubly exponentially many. They may have exponential degree. And so that's not how we want to do it. But we do want to use this in the analysis. It turns out that suppose that here with the one and the height is the size of the coefficient of the polynomial is h, then when it's an integer polynomial, so the value of the polynomial at any point is at least one, a non-vanishing point, at least one. And it's bounded by just count over all all monomials, and you have that. So you get a bound, you have a lower bound on V there. Okay, so then that's the key. That gives the bound we saw. If you have the right degree and height bounds, so degree comes in all these actions of reductive groups, there is an exponential bound. So that seems to be exactly what we need. Bigger would not be good. And for the bounds on the height of coefficients, we need to prove it, but it follows from something called the omega process divided by Cayley. This is a 1850 paper, which really opened up, I mean, invariant theory, the first paper. It says amazing things in it, including this omega process. But basically, you get, in these cases, which we have, you get a lower bound on the L2 norm, which is one polynomial in D, which will be one exponent. So that sort of does this generalization to group actions on tensors. Okay, here's some questions. I mean, we should have asked them even earlier. This sort of greedy process starting from a synchron algorithm for matrix scaling. And in this setting in particular, where the groups are like GLN, are certainly not a convex object. You're solving an optimization problem, and such a greedy algorithm converts. How does it work? Why? We'll see why. And I promise you that scaling and null cone are dual to each other. I'll explain why. And it also raises the question, once we can deal with group actions, it seems that we can deal only with cases where at least two groups or products of groups is acting. What suppose just one group is acting on a vector space, like conjugation? There's no alternating anything, there's only one group. What do you do in this case? So we'll answer all these questions in the next round of generalization. So let me ask for questions first. Okay, so we want to understand this and have more generalization of the algorithms we saw. I want to talk about this non-conductive duality theory, geodesic convexity, the moment mapping with all these guys. So back to these two examples, now we know that we can analyze everything with L2 norm, but in fact, I want to think about where we had this goal in these two problems was scaling, and the analysis had to do with minimizing the L2 norm. I want to switch the analysis and the goal. Let's look just at this optimization problem of minimizing the L2 norm. So we have any group acting on matrix group acting on vector space, and a natural optimization problem which we saw, namely the question of the narco, is minimizing the L2 norm of GV for all GV group. Okay, so in other words, if you look at this orbit, we are given a point and we are looking for the lightest vector in the orbit, ask whether it's arbitrarily close to zero or far away. Now, okay, so this is the optimization problem, it's not convex. The question of whether it's zero or not is an outcome problem, this we've seen all. Now, we are looking for an efficient algorithm for it, but thinking like computer scientists, if you don't see obviously a polynomial time algorithm, the first thing you ask is it in NP, is it in NP? So how would you convince someone that the infimum is zero, that it's in the null cone? At least informally it's in NP, informally in the sense that I can give you a sequence of group elements that gets it closer and closer to zero, as close as you want. So that would be an NP group. How do you convince that this is positive, this infimum? That's not obvious. I mean, one way to do it, if it's not in the null cone, one way to do it is to give an invariant polynomial, but how do you find it? Well, it may be exponential degree, so double exponentially long, and the answer is this amazing duality theorem of invariant theory, which is the Kemp-Nash theorem. It says that the infimum is positive, you are not in the null cone, if and only if something else is zero. What is this something else? This is a moment map where I have, So if another thing, there is a point, this point which is closest to zero there, where mu of V star is zero. What is mu? Mu is just the gradient. In this setting, the gradient is called the moment map. So it's something which non-commutative, which in the commutative case is a gradient, but it's the same intuition. You found the local minimum. In this case, you cannot support zero. So you'll see an example. It turns out that minimizing the vector with the smallest moment map, you ask whether it's zero or not. Zero here is the vector, right? The gradient is the vector. It turns out to be a scaling problem, so I'll show you an example. So that's the duality between null cone and scaling problems. So in other words, scaling problems arise in every such setting, even if they were not defined from application. But the important thing is really this, what does it mean that you have this duality? You have a local condition, you found a point with zero gradient, and this means that you are at a global optimum. When do we see such things? Only when the structure is convex, right? But this is this hint or tells you what to look for. Convexity, it's just that convexity happens to be in a more general sense than Euclidean, so where shortest paths are not lines, but some other curve. And this suggests extending the framework of Euclidean convex optimization to some Riemannian manifolds that arise here. So that this convexity, this duality theorem, which implies certain convexity, really explains why the greedy algorithm. It's I'm just saying it keeps improving things, but it will never get stuck at some local optimum which is not global. At least that, so.
Could you say something? I'm not understanding. This function mu, it depends on the initial vector v, or is v star that depends on the initial vector v?
No, mu is a function on the space, on V, capital V. Okay.
Yep.
And we are interested in its value along the orbit, its minimum value along the orbit. Okay. So V is in the null cone if and only if there's a non-zero vector which has a zero gradient. So the optimum is not zero. I have something more about maybe the moment map, well, not much, but yeah, so it's like in the Euclidean case, you should really think about it as a gradient. I mean, it's what you look is that you are trying to, just like when you define the derivative, it's a gradient of moving a point by a group element which is close to the identity. Right, moving it by epsilon. It's always a linear function, like the gradient. So gradient is a linear function, but it lives, when you do it in Rn, you get a vector in Rn. When you do it in over a group like GLN, you get it in the Lie algebra of the group. I'm not defining it, but let's say in the case of GLN, this will be the space of Hermitian matrices. So it's a linear space. Moment comes from momentum, it all comes from physics, this notion. And yeah, I mentioned that on an orbit, minimizing the gradient is equal to minimizing the vector itself, namely whether it's in the null or not. And I'll show you examples why minimizing the gradient is a scaling problem. What are the examples? It just, for these two examples, if you don't look at these problems as, you have an object like a matrix or a couple of matrices and you act on them with this group, and you ask what is the gradient, if you just compute it, which is easy to do in these two examples, this is what you get. Here you get two vectors of length n, so a vector of length 2n, which is a times 1 minus 1, and a transpose 1 minus 1. In other words, scaling problem arises just, it's minimizing the moment map for this action, and there the moment map happens to be exactly the scaling problem for the operator scaling. So it just computes the moment map and out comes the scaling problem. Yeah. Okay. So when the moment map is zero, that then you can, for a non-zero vector, then you can, this vector is scaled. Okay. So I want to start going to the last generalization, which is this geodesic algorithm. Geodesic, algorithms, convex algorithms are not new. The convexity is all nice. The Gauss, I think, is easier, and Riemann, well, most people also. And even the geodesic algorithms, there are books on geodesic algorithms. What we have here is for this family of problems of null cone, and you'll see more. We have, efficient algorithms. I'll tell you what we have algorithms for. I have here just for people who've never seen it, even though I'm not sure this will be too helpful. It's just that when you do analysis in, you do first year calculus, you have the derivative of f of x minus f of x plus delta divided by delta, and you take delta to 0. It's better to think multiplicatively for all these definitions, really to multiply by 1 plus delta. So really, directions you should think of as the exponent. So a direction, if it's a vector h, you put it in e to the h, you write it multiplicatively, and usually you put it along the diagonal of the diagonal matrix. Or in a non-commutative case, it will be represented by, as I said, the Lie algebra by a vector which is arranged in a matrix. I drew a curved space here, which is a ball, but that's not how the curve spaces we deal with look like. But anyway, of course, you can linearize this. That's a 1 e to the epsilon is 1 plus epsilon. And this happens also with Maass. And straight lines look like this. You start at a point, let's say, the identity, and here you multiply it by e to the th when t is the parameter, so that in the exponent it's a straight line. In the non-commutative case, you do the same. So what's a straight line? A straight line, one way to say geodesic and Euclidean geometry, if you draw a straight line for a point, you see all points for which the closest way to get to the original point is along the line. That's what geodesics are in general. If you start at a point in this space and multiply by e to the th, now h is a matrix, then you turn out in space, you will get some curve in this manifold, you will get some curve. And this curve will represent exactly the same. Every point on that curve is closest path to the original point we started with will be along that curve. It will be a geodesic. And now convexity is defined along geodesics in general. Euclidean, now Euclidean, you do this, right? I mean, you want a function in the average point along the geodesic. In the average point will be at most the average of the values in the triangle. It's the same definition. And once you know that the function is convex, you can apply these standard algorithms. In first order algorithms, I give you the gradient and you move along the gradient to minimize the function. You have to pick, of course, how much you move, and that depends on properties of the function. In the second order convex algorithms, you basically approximate, you get the Hessian as well, so you sort of approximate your function by a quadratic. And this no minimization, the problem we talked about, happens, and it's easy to prove to be always convex in this sense. Okay, just always convex, so we are in a convex set. And so summarizing the understanding here is that now we can deal with any group action on any vector space when we have such an action and we are given a vector in space, an epsilon parameter, and we may want to approximate either the L2 norm of the lightest point in the orbit or minimize the gradient. We showed that they are dual to each other if you want the exact answer, but if you want approximation, they're actually different problems, and we needed to extend also this duality of every quantitative version of this duality theorem I showed you. But anyway, you can run algorithms in the same way, first or second order, you get the action and the appropriate derivatives. And in general, in this setting, and now we don't need products of groups, any groups. We have a variant of first order method, which converges in polynomial types, which is just like in the Euclidean setting. We have a version of the second order method, which converges exponentially, like polylog 1 over epsilon in general, again, like Newton's method. And so the nasty thing, actually also in the Euclidean case, is what's the constant in this algorithm. So it's all polynomial or polylog, that's very nice. What's the constant? And also in the Euclidean space, of course, it depends on how smooth the function you minimize are, how convex it is. And we know what are these parameters in Euclidean setting. Here it's more complicated because to understand the smoothness, you really need to understand the action, which is a representation of the group. You have to decompose it to its irreducible representation and look at the geometry of the weights of these representations. I want to say that the computation may be complicated, but the dependence of the constant on these parameters is very small. So just two parameters you need to know, and then you get these boundaries. Of course, sometimes it's good, and sometimes it's not so good, and sometimes we don't know how to compute. Okay. very good, lifetime. I wasn't sure I get that. I want to tell you about problems a little more general than null-count problems that can still be handled by this technique. And this has to do with the non-uniform scaling I talked about in the beginning, like with non-uniform marginal, for example. And how they relate to the moment map and what I define moment point. Okay, so again, we have an action on a vector space, and we have the moment map, this non-commuting gradient. And what is, again, I'm repeating what I said, what is the null-count problem or the uniform scaling problem? You want to know, given a vector v, whether there is another vector u in the orbit which is 0 or not, whose gradient is 0, right? In this case, it's not in the null. But you can ask not whether it's the gradient is 0, you can ask whether it equals some other vector. And in fact, this corresponds exactly to non-uniform scaling. Right? So 0 happened in the matrix scaling like a times 1 minus 1. This way you want it to be 0, but you may want to be something else or something. This leads to questions of this type. So you ask whether there's any point in the orbit which has a gradient that looks like this. That's a non-uniform scaling problem in general. And how do you approach this? Well, here's a nice object. Let's look at all the gradients that occur along the orbit. Set of vectors in some vector space. So this delta of V are all the points which are gradients of something along the orbit. Okay. It turns out that you have to remove, I mean, this is not the right definition, you have to mod it out by some unrelated group, the Y group, and which, it doesn't matter anyway, but essentially it's all the gradients in the orbit. And then something really mysterious happens to me, it's something that's, now I understand it better, it still blows my mind. What is this set? It's a set of vectors, but it turns out it's always a convex polynomial. This is a very deep understanding to it's a series of things that were understood first for Torus section for the Euclidean case, which is really the case in physics, and then in general, this is always a convex polynomial. So I don't know if, this was the first time I met a polytope that was not described either by its vertices as a convex half set or by defining hyperplane. But these are convex polytopes that are born this way. That's so mysterious. And what are we asking? We are asking whether a vector P is in a polytope like that, delta of P. This is so these are general marginal problems or membership in moment polytopes, and we have algorithms for this as well. Okay, in fact, the Brass-Complete computation is really of this nature. It's not a null-count problem, it's a moment polytope. It's Brass-Complete polytope or moment polytope. So I just want to give you some examples of such moment polytopes because they are really, you see how strange they are. So you see, I have two types of examples. Here's a set. Given a symmetric matrix, think of the vectors which are the diagonals of a matrix which is similar to A. So you conjugate A, you look at the diagonal. Okay, conjugate it in all possible ways. You get a set of vectors that are diagonal. This is the convex set. It's convex polytope. This you can prove it. But you wouldn't, it doesn't seem like, obviously why it has to be like that. It's a sure Horn polytope. Here's one which is much more mysterious, the Horn polytope. Suppose you have three symmetric or Hermitian matrices, so A, B, and C, so that A plus B equals C. Okay. And look at this set of eigenvectors, all in sorted order, lambda, lambda. It turns out that these tuples, so these vectors of length 3n, form a convex polytope. Within, yeah, okay. So the group action is obvious. I said similar to conjugation, and if I conjugate it also, we have the same equation. It's not clear why they are polytopes. On the other hand, you have a set of polytopes that are obviously polytopes, and it's just not clear what the group is. Here's a famous polytope, the Newton polytope of a polynomial or Laurent polynomial, maybe some negative exponents. Take the convex half of all monomials of the exponent vectors of the monomial which you see. So it's also it's obviously a polytope. Here's another famous polytope. It's a polytope for the mesoid intersection problem. Anyway, a famous polytope. And, I mentioned the Basquiat-Lie polytope. It is satisfying some inequalities for all subspaces. In these cases, the polytopes are given as polytopes, but it's not clear what the groups are, or it's not obvious that you should look for groups, or that looking at group action will help you understand that. But it turns out that it does. So, yeah, so let me summarize that. So what did we see? Well, we saw lots and lots of areas of Maass creeping in as problems and tool providers and applications. Even though we started from really the initial problem that we started with, I didn't even mention in the list of authors, or maybe I did. It's a paper from 2014 with Pavel Hubesh, where we just try to understand the question of arithmetic circuits in non-commutative variables. We wanted to understand whether one can remove inverses if you are computing a polynomial. If you are computing a polynomial using inverses, what is a good example? When you compute the determinant of a matrix, you do Gaussian elimination, so you divide, but the output is a polynomial. Do you need a division? Does anybody know? Can you do it? Yeah, I know you know. It's not obvious. It's not obvious at all. But it turns out that one can efficiently compute the determinant without division in also in polynomial time, polynomial sets. And this is a general result of Strassen, that whenever you have an arithmetic circuit with commuting variables in which you compute a polynomial but use division, you don't need the division. You can make it, you can compile this circuit to another circuit which computes the same thing and does not use division. We were asking ourselves the same question for non-commutative variables, and this at least what brought me to this non-commutative singularity problem. But anyway, then we met all these lots of other areas of math. Something strange that happens in this operator scaling and some other problem. The non-commutative singularity problem is obviously an algebraic problem. It's about the inversion of a symbolic matrix. It's a symbolic problem, but the algorithm here is really dynamical. It's really an analytic type of algorithm. So yeah, it's and on the other hand, to analyze this dynamical algorithm, you use tools from algebra, from invariant theory, representation theory, so on. Understanding that there are group actions behind some problems that don't really show it is can be very powerful. And yeah, what is there to do? There are plenty of problems here. There are concrete problems, but generally, one thing is that, as I mentioned, not all these algorithms are polynomial time. For example, even tensor, 3 tensor scaling, scaling 3 tensor. We don't know a polynomial time algorithm. I really hope that there'll be more applications that are of the combinatorial optimization nature, like matrix intersection. That may be the most general combinatorial problem that I know how to solve with these tools, and anyway, it's solvable, right? So we don't need it. There must be more, but I don't know. And I solved lots of null problems. It's possible that the null problem in general for any group action of the sort is in polynomial time. We don't know. There is a result showing that it's always, it's a variant of this, but I'm not going to define it exactly, but essentially the null problem is in NP intersect quantity. So this movie there, Walter, somebody else. Maybe a general polynomial time algorithm. It would be amazing. We'll solve lots of problems at once. And back to the problem I really care about, which is a commutative singularity. The question is whether it has a deterministic polynomial time algorithm will mean that low bound, be different NP in some sense. One thing you can ask yourself, I should definitely ask that. Does it have, is it an algorithm? I mean, this is also an algebraic variety, right? The set of symbolic matrices for which determinant is 0. It's really an algebraic variety. All the coefficients of this determinant should be 0. It's an algebraic variety. This is the null cone of some group action. Then maybe we can hope to use one of these gradient descent like algorithms and maybe analyze it. Well, it turns out that it's not. Somehow, this is the first time I think I know of a difference between the commutative and non-commutative singularity, which is mathematical. It turns out not to be an outcome problem. Namely, there's no group action on the space of capital matrices, for which those that are commutatively singular are an outcome. It's just not an outcome. Proving this is not trivial. It has to do with, you have to understand the symmetries of a variety, and even in the cases you have only one matrix, this is work of Frobenius, and yeah, I'm sure everybody knows that the only symmetries of determinant is that you can change bases on the left and on the right. It doesn't change the determinant, and there's one more group action. What is it? Transport. The two also are right when it's transported. And these are all the symmetries. That's the result of Frobenius. To prove this, you need to do the same for tuples of matrices, and you actually get even a different proof even for the one case, for the one matrix case. This was with Mark. Anyway, let me finish. That's my ending slide for every talk. If you, those of you who don't know enough, they think about computational complexity, should take a look at this. It's very friendly and it's free. It's on my website. Thanks. Okay, questions?
A question about whether null concept all the time, would that follow if you had sort of much better degree bounds for invariance?
Sorry, say again?
The question about whether the null cone is followed all the time, would that follow if you had, better bounds for the degrees of invariance?
Yeah, that's a very good question. It's entirely possible. For the analysis of this algorithm, the exponential bound is enough. And I said that this algorithm works in characteristic 0. I mentioned that there was an algorithm by Ivanov and Subramanian, which is very different and works for everything. This algorithm is just for operator scaling, like for non-commutative singularity. is algebraic in nature. You can think of it as an algebraic analog of augmenting path in bipartite graph. And what it needs is a polynomial bound on the generating invariant, in this case of left-right action. This bound is very recent. It was partly motivated by this work. Actually, it came as a consequence to this paper of Herbert and I that I mentioned about inversion in non-commutative formula. We needed that bound, and it was proved by Derksen and Markham in about 2015. So, because it exists, Ivanov-Skar and Subramanian were able to design, analyze, and get a polynomial. In this case, it's just a different polynomial time algorithm. But better degree bounds, when they exist, can have different algorithms. Yeah. I don't know if a concrete application for which this doesn't work, but that's supposed to work. And in general, this exponential bound is that there are many group actions for it. Oh, nice. Yeah.
So is, low-pass has this randomized algorithm called the commutative singularity, and so is that easy to describe?
I described it.
Okay.
You want to know whether a symbolic matrix is the determinant vanishes or not. Plug in random integers, let's say between 1 and 100n, or 100n squared, right, for the variables, and evaluate the numeric determinant. Numeric determinant is no problem to evaluate. And if the determinant was identically 0, you will always get 0. Right? If it's not identically 0, the probability that you land on a 0 is vanishing this moment. That's the whole algorithm. It was really an observation. The principle is what is sometimes called the Schwarzschild lemma. But it's if you have a low degree polynomial, a random value, and it's not identically 0, random values will show this to you. Okay. Thanks.